Hello, everybody. So we, Tabashi, Leo, Lily, Ziming, and Saurabh, and me, Eleonora, we looked at machine learning techniques to turn rotational lines into powerful diagnostics of physical conditions inside giant molecular clouds. And for that, we looked at the nearby giant molecular cloud, ORMB, which you can see here in the background. To set the scenes, so as we have heard in the lectures this week, molecular clouds are highly hierarchical structures with which fragments into higher density regions, the filaments and cores, where star forms. And as the most abundant molecule, the H2 cannot be observed in a submillimeter due to its homonuclear nature, we have to make use of other molecular lines and other tracers to look at the physical conditions.
So the goal of our project is to estimate the molecular gas column densities in the Orion B giant molecular cloud. And the motivation is that we hope to produce these density estimates that are more rigorous than commonly used methods currently. So super brief overview of commonly used methods. One is we often use the CO line intensities. We assume a linear relationship multiplied by a constant value, and then we get molecular gas density estimates, or we can use dust observations, do SED fitting, which we've heard a lot about, get the extinction values, and then again, multiplied by a constant and get molecular gas density values. So our aim is with random forest and principal component analysis, as well as using all the data which you'll hear about, is to provide density estimates that are more reliable.
So I will quickly describe the data. So we were provided the IRON-B program data, which stands for Outstanding Radio Imaging of IRON-B. So these data were acquired with the 30-meter IRAM telescope at a resolution of less than 0.1 parsec and a spectral resolution of less than 0.5 kilometers per second. So we were provided like 12 spectral cubes. And with this spectral cube, we did an integration for each pixel. So we were provided this spectral. And using GILDA software, we integrated the spectra and we computed the noise level and the peak temperature. So we have all these data, so these 12 spectra, and basically each line will probe a different density of the molecular cloud. For example, 12CO will probe the outer region, while N2H plus will probe the denser region.
So, okay. To get a first understanding of the correlations that we can find in our dataset, we applied principal component analysis, PCA for short. And what we are especially interested here is the first principal component, which gives us the direction of largest variance in our sample of 12 different integrated line intensities. So as you can see in the top plot, the first principal component is the one with the largest component. And what's interesting to note is that all of our 12 lines contribute positively to it. So this implies that there are some kind of underlying physical processes which could be similar for them. Now, to test our theory, we plotted the PC1 component against the column density of H2. And what you can nicely see here that there is in fact a trend, but it's not a linear trend, which we would like to have. Therefore, we moved on to a more sophisticated method.
Yeah, so to better predict the column density of H2, we use the random forest method. It is a supervised machine learning method that have a lot of decision tree and combine them to get the final results of the column density. And here in the left, you can see that we use the whole image that predicted from the dust as the reference, except the red square in the right of it as validation. And we use the random forest to predict the result is shown in the middle figure. And you can see that just by eye, it is quite well consistent with the reference. And if we plot the ratio in log space, you can see the ratio is quite close to 0, means we are getting a good results. And when we compare our result from the random forest with the result from the traditional CO to H2 conversion factor, we can see that our result have a much more linear relation with the reference column density. And it also have a smaller bias and smaller standard deviation.
Yeah, so after 13 days of hard work and fun time, we could conclude using the machine could predict using the random forest technique that column densities are estimated to a factor of 2 as compared to the other traditional method, XCO method, would do it by a factor of 10. So now what should we do further? The future goals can be that to prove the generosity of the machine. So for that, we need to use this machine on other nearby molecular clouds like Orion A, Taurus, and Perseus. But if it doesn't work, then we have to train the machine on them as well. And what about the other galaxies? Since these results might be, relation might be metallicity dependent, maybe we need to train the machine on other galaxies and increase the data sets. Okay, thank you. And I thank my supervisors, and yeah, thank you.
Questions? Okay. Maybe you can keep one. Oh, doesn't.
Thanks. In one of the very first figures, you showed the data or the spectra next to each other, and there was some very obvious correlated noise in all of them, some lines probably from scanning artifacts. How does the machine learning algorithm, such as the random forest, react to this kind of correlated noise? I assume it is very much poison for those, right?
Yes, so we still include noise in the random forest algorithm. The reason is for like 12CO is quite strong, but for other emission lines, if we exclude the noise, then it will be a very little part that not representative for the whole data. So we still include, and as you can see in the results, it predicts pretty good.
Other questions? So you worked with the column densities, but did you have some tracers that would give you access to other parameters, density, temperature, things like that?
For the random forest?
Yeah, I mean, for any of the methods that you have
yeah,
tested.
so we are using all this 12 intensity as well as the 12 peak temperature. Yeah.
No more questions. That's a question. Yeah. Bye. Bye. Bye.
Actually, other principal component represent other physical properties. They probably represent other physical properties, but we don't have time to check that. Yeah.
Okay. Thank you.